Okay, I'm going to be going over the second semester chemistry practice final. The first problem is a stoichiometry problem. What mass of silver oxide is required to produce 25.0 grams, by the way? That zero right there is significant, so this is a 3 sig fig. And it's seeing as it's the only number given, that would mean that our final answer should be rounded to 3 sig figs. Of silver sulfadiazine. Ooh, hard one. So that compound right there. This is a stoichiometry problem, and what we're going to do is we're going to start with the number given. So that would be the 25.0 grams of silver sulfadiazine. Let's just abbreviate that to SS for short. And we're going to multiply that by, well, we're going to try to cancel the grams of silver sulfadiazine and get us moles of silver sulfadiazine. And then we're going to need the molar mass of silver sulfadiazine. All right, I got that molar mass of silver sulfadiazine, and that's 357.4 grams for every 1 mole of silver sulfadiazine. And then the next step is we're going to multiply by a ratio that's going to cancel. So actually, first off, we've canceled the grams of silver sulfadiazine. And we're going to now multiply by a ratio that's going to cancel moles of silver sulfadiazine. So that's what we're going to cancel. And we're going to need moles of, well, what we're trying to go to, which is the silver oxide. So 2 silver, 1 oxygen atom combined together give you silver oxide. We need to know the mole ratio. So silver oxide currently has nothing in front of it, and sulfadiazine has a 2 in front of it. So there's a 2-to-1 ratio. 2 moles of silver sulfadiazine for every 1 mole of silver oxide. Lastly, we need to convert from moles of silver oxide into grams of silver oxide. So we're going to need to multiply by the ratio, which is going to have grams on top and moles on bottom, and that should look familiar. That is molar mass. So this is going to be the molar mass of silver. Whoops, put the do in the wrong place. Silver oxide over the moles of silver oxide. That's going to cancel moles of silver oxide and give us finally the grams of silver oxide. But we need to know the molar mass. Now, just a review of how we get molar mass. Now, I looked up the molar mass of silver sulfadiazine, but you might not have the molar mass or the capability to look up molar mass on a test. So we need to know, how would you do that? What we're going to do is we're going to take the molar mass of silver and multiply it by 2, and then add that to the molar mass of oxygen. So for that, we're going to need a periodic table. Here we go. Here's a periodic table. We need to know the molar mass of silver. So let's see, silver is right here on the periodic table, 107.87, and oxygen is 15.999. So we're going to open up a calculator and do 100, and I already need to remember what the number is, 107.8. Yes, 107.87 times 2, because there's 2 silver atoms. And then we're going to add to that just the molar mass of 1 oxygen, which is 15.999. That gives us 231.73. So since we're going to round to 3 sig figs anyways, let's go only 5 sig figs right now. So 231.74. 231.74. Last step to do is just to multiply everything out. So since we already have this number here, we'll start there, but the idea is we're going to multiply everything on the top. So we're going to take our previous answer of 237.71 grams, And we're going to multiply by all the way on the left side, there's that 25 grams. And then we're going to hit divide, and we're going to divide by 357.14. And we're going to hit divide again, because we're still dividing because it's on the bottom there, the 2. And what we get is 8.111. We're going to round to 3 sig figs, which is 8.11. So we get 8.11. And this was, of course, grams of silver oxide. The next problem is a limiting reagent problem, or limiting reactant problem. So our plan here is we are going to determine how much C7H16, how much carbon dioxide, should be clear, how many grams or how many moles of carbon dioxide C7H16 can make, and O2, or oxygen, can make. And whichever one makes the least amount of product is going to be our limiting reagent. So all we're going to do is do 2 stoichiometry problems. So we'll set up the first one with the C7H16. So we're going to start with how many grams of that? 250. Now notice that 0 right there is significant, so you get 250 with 4 sig figs. That's going to be important for the ending part. Let's start with the 250.0 grams of C7H16. And we're going to multiply that by, this is basically just like a stoichiometry problem. We're going to take the molar mass, and we're going to divide by the molar mass in order to cancel grams and get us into moles. And this is, again, of C7H16. C7H16. For every 1 mole, molar mass always has 1 mole. So I looked up the molar mass ahead of time. We have the 100.2 grams per mole. So it's 100.2 grams for every mole. And then we're going to multiply by another ratio, and this ratio is going to turn moles of C7H16 into moles of carbon dioxide. And just a note, we cancel the grams, don't forget to cancel them. So we want moles of C7H16 on the bottom, and we want CO2 on the top. We need to find moles of CO2, that is. So we need to find the ratio that converts moles of CO2 to moles of C7H16. We're going to find that from the balanced chemical equation. CO2 has a 7 in front of it. C7H16 has nothing in front of it, which means there's a 1 in front of it. So we get 1 mole of C7H16 to 7 moles of CO2. That cancels the moles of C7H16. And now finally, that is going to be it. We do not need the last step of stoichiometry. So the last step of stoichiometry would be to find grams, but we don't need that. We just need moles of CO2, because we're answering the question how many moles or how much CO2 could be created from those 250 grams of C7H16. So all we need to do is plug that in a calculator, but we're going to have to do this again anyway. So let's set up the next problem before we plug in the calculator. We're going to need to figure out how much CO2 oxygen will create. So we're going to start with the amount of oxygen, which is 50.0. That's 3 significant figures. Grams O2, and we're going to multiply by 1 mole of O2 over the molar mass of O2, which, if you round it to 4 sig figs, is 32.00 grams per mole. Remember, this has units of grams per mole, but when you're putting this on the bottom, the grams goes with the number, and the moles is going to wind up being on top. All right, then we're going to multiply by, remember that cancels grams of O2, so this is of O2. And then we're going to multiply by the mole ratio, and the mole ratio for O2 to CO2 is 11 moles of O2, and you generally put what you have on the bottom and what you want on the top. So this is moles of CO2, which would be 7. So it's a 7 to 11 ratio. Moles of O2 cancel, you get moles of CO2. And now we're comparing apples to apples because we have moles of CO2 in both cases. So now we just need to plug it in the calculator. All right, plugging the first one in the calculator, we have 250 divided by 100.2, and then multiply by 7. We can ignore the ones, so we get 17.465. This was 4 sig figs to start with, so we're going to round to 4 sig figs, which would be 17.47. 17.47. That is moles of CO2. And we're going to do the same thing with the other one. So we have 50 divided by 32, and then multiply by 7, and then divide by 11 equals 0.994. That's 3 sig figs. We want 3 sig figs, so that works. 0.994. 0.994. And that is, again, moles of CO2. So now, which one created the least amount of moles? The oxygen did. So the answer to this is pointing out which one is the limiting reagent. So for that one, you're going to write O2 is limiting. And that's the answer. If we go to part B is asking about, okay, now what if 100 grams of CO2 were actually created? What was the percent yield? So percent yield, the equation for this is percent yield. The equation for this is equal to the actual yield divided by the theoretical times 100% just to turn it into percent form. The 100 grams of CO2 were actually created. So that's our actual yield. The theoretical, though, is how much should have been created. For that one, we need to consult the previous answer. So we should have created 0.994 moles of CO2. This is how much should have been created. We can't create 17.47 moles of CO2 because as soon as we create 0.994 moles of CO2, we run out of oxygen, so the reaction stops. So this would be our theoretical yield, but it's not in the grams that we expect. So we have one step that we got to do. We got to take that 0.994 moles of CO2, and we got to convert it into grams of CO2. So we're going to put 1 mole of CO2 on the bottom, and we need the molar mass of CO2. So the molar mass of CO2, we have carbon is 12.011, oxygen is 15.999. 12.011, and that is just one of them, plus 15.999 times 2, and this equals 44.009 grams. So we need that calculator back out. We're going to take that number and multiply by the 0.994 number, and we get 43.7. So 43.7, and we're going to round to 3 sig. Well, this is an intermediate number, so we're going to keep some extra digits, actually. We'll do the 4 or 5. We can keep extra digits for right now because we are going to round to the very end. And this is grams of CO2. So now we're going to place our actual yield above our theoretical, so the percent yield is going to equal, the actual yield was 100.2, 15.0 grams of CO2, and the theoretical was 43.745 grams of CO2. And then we're going to multiply it by 100% just to turn it into percent form. Let's calculate that. We got 100 divided by 43.745. And then multiplying by 100 is also the same as just moving the decimal over to the right 2 spots. So we have 229. 229%. We're going to round to 3 sig figs because, actually, are we? That's a good question. Yes, because we had 3 sig figs up back of this problem. 3 sig figs. And the reason we had 3 sig figs is back over here. 3 sig figs. All right, and that is how you do problem number 2. Empirical formula. It's been a while since we dealt with that. What we're doing is we're starting with a percent composition and figuring out what the empirical formula is. The very first step is we're going to take all of these percentages and we're going to turn them into grams. Literally just write that many grams. It's like if we had 100 grams of the total substance, how many grams would be carbon, how many grams would be hydrogen, how many grams would be oxygen. So let's start with the carbon. We have 40.0 grams of carbon, and the hydrogen is 6.714 grams of hydrogen, and 53.28 I need to have that be 53.28 grams of oxygen. And what we're going to try to do, in order to get empirical formula, let's remind ourselves, empirical formula is something like H2O. It is the lowest ratio of the subscripts. 2 and 1 is the lowest ratio you can have while being whole numbers. And it's the ratio of the subscripts. So we need to know how many molecules or how many atoms of hydrogen for every 1 atom of oxygen. To do that, we're going to need to find moles first, because moles is an amount of something. So we're going to convert all of these gram amounts into moles, which this is now the third problem that we've had to do, where we're going to have to convert grams to moles and moles to grams. So hopefully remember that in order to convert grams to moles and moles to grams, you're going to use the molar mass. So we're going to have 1 mole on top for all of these. And then on the bottom, we're going to have the molar mass. So for carbon, it's 12.011 grams of carbon. For hydrogen, it's 1.0079, I believe. And that is grams of H. And for oxygen, it's the 15.999 grams of oxygen. Notice it's just O, not O2. So in the other problems, it might have been O2. So watch out when it's O2 versus O. All right, let's plug it in our calculator. So we have 40 divided by 12.011. That's going to equal 3.33, and this is moles of carbon. And then we have the 6.714 grams, divide that by 1.0079 equals 6.661 moles of hydrogen. I'm not too worried about sig figs yet because that's not our final answer. Also, this number right here is for sig figs anyways, and so is this number. And then the last one is 53.28 divided by 15.999. And that gives us 3.33 moles of oxygen. Now, we should already see something suspicious going on here. Take a look at these numbers that we have. We have 3.33 moles. We have 6.661 moles and 3.33 moles. These two right here are the same. And hydrogen seems to be about double that of oxygen and double that of carbon. I can bet that our answer is already going to be carbon H2O. But the method for how you figure that out is you divide all of them by the smallest number. The smallest number is 3.33. So we're going to divide all of these by 3.33. And what we're going to get is that this is equal to 1, this is equal to approximately 2, and this is equal to 1. So the coefficient for carbon is 1, hydrogen is 2, and oxygen is 1. So in the end, this is the empirical formula. So that's problem number 3. Problem number 4 is finding the percent composition by mass of this compound right here, C12H22, oxygen 11. We're going to round to 3 significant figures. So this time I'm telling you what to round to because there's no number provided. There's no measurement provided. So we're just going to have to round to whatever I tell you, which in this case is 3 sig figs. How you do percent composition is you need to take the mass of one of the elements, for example, mass of carbon, and divide by the mass for the entire compound. So we need essentially how much mass is carbon and divide by the entire molar mass of the entire compound. So we're going to have to do some math aside from there. Let's find out carbon's mass. So we're going to have 12 times whatever the molar mass of carbon is, which actually happens to be 12.011. So that's going to be the mass of carbon. The mass of hydrogen is going to be 22 times the mass of hydrogen, which is about 1.0079. And then the mass of oxygen is going to be 11 times 15.999. All right, take out the calculator again. And we're going to do 12 times 12.011, should be close to 144. Yep, 144.132. We're going to keep some extra digits right now. 22 times 1.0079 equals 22.174. And then finally 11 times 15.999. And that equals 175.989. And then if we want the molar mass for the entire compound, we're going to just need to add them all up. And we'll get the molar mass of the entire compound. So add the previous answer to 22.174 plus 144.132 equals the total molar mass of the entire compound is 34.295. All right, now that we got that number, we can come back to here, and let's take a look at carbon's percentage is going to equal the mass of carbon divided by the total mass of the compound. So we're going to put this over 342.295, and that's grams, technically grams per mole, so because we found it as the molar mass. And the top is the mass of carbon, which is 144.132. Now, we said this was going to be a percent composition by mass, so we need to do that final step of multiplying by 100%. which is just moving the decimal over 2 places. I never actually type in times 100 in my calculator. I just move the decimal 2 spaces over. All right, let's do the same thing for hydrogen. So I'm going to skip that step. Hydrogen, we have 22.174 divided by the 34 point, or 342. That decimal point was supposed to be over here. All right, so 342.95. It's grams per mole on the bottom and also grams per mole on the top. I forgot to write that, grams per mole on the top as well. All right, and I did it again. I didn't write the times 100 because I almost never actually type in times 100. And then lastly, the oxygen. Total mass of the oxygen was 175.989, and we divide that by 342.95. Again, the same units of grams per mole times 100% equals, let's lay out the calculator here. All right, 144.132. Didn't get all my digits. 144.132. Divide that by 342.295. And it didn't get the decimal points. Dots. There we go. 295 equals. Oh, looks like there was an extra 2. There shouldn't be an extra 2. Let's try that again. Erase this extra 2. 3, 4, 1. Restarting because I realized there was an extra 2 in the total molar mass that shouldn't have been there. So 144.132, and then divide that by 342.95 equals 0.42, but again, we're multiplying by 100, so we're going to move the decimal spot 2 times over, and what we're going to get is 42.0%, because I said 3 sig figs, and that would be 3 sig figs. Let's do the next one, 22.174 divided by 342.95 equals, move the decimal 2 spots over, 6.50%. Lastly, 175.989 divided by 342.95 equals, move the decimal 2 spots over, 51.3%. That would be the percent composition by mass of carbon, hydrogen, oxygen for this compound. All right, that was problem 4. Problem 5 is about hydrates. So the idea is that we want to write some kind of formula. We'll write it over here. That looks like this. Magnesium sulfate, a dot, some number, H2O. So it's how many water molecules for every 1 molecule of magnesium sulfate. We start with a mass of 307.0 grams, and a final mass after heating is 150 grams, which means we've lost some mass. And the mass that we've lost is the mass of water. So that's why the first step is to determine the mass of water lost. So we're going to take the 307 0.0 grams and subtract out 150 grams, which is going to give us about 157 grams of H2O. So that's how many grams of H2O. And we also know how many grams of just magnesium sulfate we have, because we, after heating it, have 150 grams. And if all the water is gone, the only thing left must be the magnesium sulfate. So we're going to write 100 grams of magnesium sulfate. And actually, let's just move that really quickly so I can give myself some more space to work. Because what we're going to do next is convert to moles. So we're going to use the molar mass of both water and magnesium sulfate. So water has a molar mass of 18 point. Now we're going to need some more digits. So water's molar mass is 18.015. And that's grams for every 1 mole of water. And then we're going to need the same thing for magnesium sulfate. And there's our molar mass for magnesium sulfate. So molar mass is 120.361 grams for every 1 mole of magnesium sulfate. This cancels grams of magnesium sulfate, and the same thing with the water, and gives us moles. Let's calculate those numbers really quickly. Now that we have moles of magnesium sulfate and water, we need to find out what the ratio of water to magnesium sulfate is. So we're going to divide both of the numbers by the smallest one, which in this case is 1.246. For magnesium sulfate, that's going to give us 1. And for water, well, we got to calculate what that is. So that's 8.715 divided by 1.246. And that's going to equal 6.994. That's suspiciously close to 7. Let's write it out. 6.994. This is so close to 7 that we're going to approximate it as 7. So there's about a 7-to-1 ratio. 7 waters for every 1 magnesium sulfate. So the final answer would be magnesium sulfate heptahydrate, so 7H2O, and you'd of course write this as magnesium sulfate heptahydrate. And that would be the final answer for number 5. Problem number 7 is to create a claim evidence reasoning that explains which compound would have a higher boiling point. So this is all about intermolecular forces. So you must mention the type of intermolecular force and the relative size of the molecules. Let's first look at the type of intermolecular force. For that, we're going to need to look at the structure of these. First off, I'm seeing that these are very symmetric, which if it's perfectly symmetric, then that would mean that this would have to be a nonpolar molecule. Because even if there are polar bonds, the polarities are going to cancel each other out, and you're going to have a nonpolar molecule. In a case where you don't have symmetry, so for example, we could take a look at this case, the hydrogen and chlorine bond. This is a polar bond, and how we know that is because chlorine has a higher electronegativity than oxygen, or hydrogen. Chlorine has an electronegativity of 3.16 and hydrogen 2.2. The difference between that is approximately close to 1, and that is definitely above 0.4, but below, so it's less than 1.7. So this falls in the polar range. And since there's no symmetry of the molecule to cancel it out, the chlorine's going to have the negative side and the hydrogen's going to have the positive side. That is just the example if do have a polar molecule, but here we do not have a polar molecule because we have symmetry. So if it's nonpolar, then that means that the only intermolecular force you have has to be dispersion forces, which are the weakest type of intermolecular force. But what's important is they both have dispersion forces. So the type of intermolecular force isn't going to matter when you're comparing the two. All that's going to matter is the relative size of the molecule. Now, these are not drawn to scale. Not to scale. But if they were drawn to scale, the sulfur trioxide over here should be much larger. This is because sulfur itself is a much larger molecule than boron. Boron's molar mass, 10.81, whereas sulfur's is 32.06. The oxygen and hydrogen oxygen and fluorine have fairly close molar masses. Fluorine is a little bit bigger, but the difference between sulfur and boron is going to be more significant. Sulfur trioxide is a larger molecule than boron trifluoride. So when creating a claim and its reasoning, the claim is going to be that sulfur trioxide is going to have a larger, or actually we're talking about boiling point, so it's not larger intermolecular force, but higher boiling point. Then boron trifluoride. The evidence. Here we're going to mention the fact that they have the same type of force, intermolecular force, and that the size of the sulfur trioxide is larger. So both sulfur trioxide and boron trifluoride have the same structure. Actually, we'll say symmetrical structure. And sulfur is a much larger atom than boron. That is just our evidence. We haven't mentioned why that evidence matters. That's where the reasoning comes in. For the reasoning, we're going to tie that together. So we're going to start with this sentence. Since sulfur trioxide and boron trifluoride have the same symmetrical structure, then they both have the intermolecular force, IMF for short, of dispersion forces. Therefore, the type of IMF does not matter. we'll follow up with another sentence. Since sulfur is larger than boron, sulfur trioxide is larger than boron trifluoride, and therefore has larger intermolecular force. Problem 8 is an ideal gas law problem. We're given moles, temperature in liters, and asked to find the pressure. So we're going to start with PV equals nRT, our ideal gas law equation. And we're going to recognize that we are looking for pressure. We're given volume. We're given the amount of moles. We're always given R because it's a constant, never changes. And finally, we're given our temperature. So we're just going to solve the equation for pressure. So pressure equals number of moles times the R, ideal gas law constant, times temperature divided by volume. And we're going to plug in our numbers. So that's 30.0 moles. And we're going to multiply that by our constant, which is 0.0821. And the units for this constant are atmospheres times liters divided by mole times Kelvin. And then we're going to multiply by our temperature, which is 50.0 Kelvin, and divide by our volume, which is 5.00 liters. Taking out the calculator, let's plug that in. 30 times 0.0821 times 50 divided by 5. Our final answer for pressure is 4.63. But now let's look at the significant figures of the problem. Looks like they all have 3 sig figs. So we're going on to the third sig fig, which is at that 6 there. So we're going to look to the right. It's 3. So it's not a 5 or greater. So we're not going to round up. So the actual answer to the problem here is 64.6 atmospheres. The next problem is also using the ideal gas law, but it's using a different version where we're talking about how we're changing from one set of conditions to another set of conditions. For that one, we're going to use P1 times V1 over T1 equals P2 times V2 over T2. This is assuming that our gas is fixed in that container, and we're not changing the amount of moles of gas. If we are changing the amount of moles of gas, we would need an N1 and an N2 underneath. We could start with this full equation, and we're noticing that we have a balloon with an initial volume, so this is our V1, and at STP, that's a key word right there. That means 0 degrees Celsius and 1 atmosphere of pressure. So we're given a temperature, a T1, and a P1. What would its volume be? So we're looking for V2. V2 is the question mark. If the temperature was increased by 40, now notice it says by 40, that means it's going to go from whatever it was before to 40 Kelvin. Now notice none of this mentioned moles, so the amount of moles is the same, so we can get rid of it from both sides. We're solving for V2, so let's go ahead and rearrange this equation. If I multiply both sides by T2 and divide both sides by P2, then I'm going to get V2 by itself. So V2 equals T2 P1 V1 all over P2 T1. Let's plug in some numbers. T2, well, first off, before we can find T2, we need to find T1. T1 equals 0 degrees Celsius, but we have to use Kelvin. So that is actually 273 Kelvin. So T2 must equal 313 Kelvin. So T2 is 313 Kelvin. P1 is 1 atmosphere. And then V1 is 15.0 liters all over P2. And I just realized that this question is not saying that pressure is changing. So we're going to assume P2 equals P1, so that the pressure is the constant, so that actually cancels here and here. And this equation simplifies down, because we'd have 1 atmosphere also on the bottom. And we'd have T1, which is that 273 Kelvin. Notice the kelvins cancel, and we get just liters left. Let's plug that in our calculator. 313 times 15 divided by 273 equals 17.198. And the amount of sig figs we had looks to be about 3. So we're going to round to 3 significant figures. So that would be that place value right there. So it's 17.2 liters is our final answer. The next problem is problem 10, solutions and concentrations. This one says, how much sodium hydroxide would you need to make a 5 molar solution using 250.0 milliliter volumetric flask? So for this, we're going to need to remember that molarity equals moles per liter. So if we can just find out how many moles and how many liters, we have molarity. Here in this case, we actually have molarity, and we have liters, technically milliliters, but we can find milliliters easily. So what we're looking for is moles. Rearranging this equation, we get that moles, that's probably the worst M ever, moles is equal to molarity times liters, or a volume. I'll put V for volume. So then we have molarity is 5.00 moles per liter. And then we need to multiply by our liters, but it's 250 milliliters, which would be 0.250 liters. And it's actually another 0 there, because there's 4 sig figs here. This is 4 sig figs, and this is 3 sig figs. So our answer will be in 3 sig figs. So 5 times 25, this should be around 1.25. Problem number 11 is a M1V1 equals M2V2, a dilution or making something more concentrated type of problem. So we originally have 330 milliliter sample of a 12 molar concentrated aqueous solution of hydrochloric acid. So what they've given is the molarity, initial molarity, and the initial volume. And we need to dilute the solution to have a more dilute, so a less concentrated solution. So that would be a later molarity, later concentration. How much water do you need to add? And notice this is add, so this is not how much water, what's the final volume of the solution going to be, but how much additional water do you need to add? That's a little bit of complication, but we'll get there. So first off, we're solving for what V2 is the first step. So let's just solve this equation for V2. We get V2 is equal to M1V1 over M2. And we can plug in our values there. So our values would be, M1 would be 12 molar, so 12 moles per liter, and then we're multiplying that by the volume. Now, we don't need to have the volume be in liters, actually. We can write 330 milliliters, and I'll show you why. So then we're going to divide by the ending molarity, so that's 0.750 moles per liter. And the reason we didn't need to convert the milliliters to liters is because if you take a look here, all the other units are going to cancel themselves, and the units we're going to get at the end is just milliliters. So our answer is going to be milliliters, which is fine. We can have our answer be in milliliters. Since we didn't have to rely on this volume measurement canceling the liters down here below, then we could just have it be whatever units we want it to be in. All right, once you get your answer there, you're going to get a final volume. Let's pull out the calculator and take 12 times 330 and divide that by 0.75, and we get 5,280. So 5,280 milliliters. Now, we originally had 330 milliliter sample. So we need to subtract out 330 milliliters in order to figure out how much additional water we need to add. So 5,280 minus 330 is 4,950. And it looks like all the numbers are at least 3 sig figs, so we're going to keep it 4,950. So the final answer is 4,950 milliliters of water. Problem 12 uses the specific heat of substances, and it's going to use this equation right here. It's going to use the Q mc delta T, or MCAT. What I mean is we're going to use MCAT equals negative MCAT. No Q, because that is what MCAT equals, is it equals Q. For one of them is going to be for water, and one of these sides of the equation is going to be for the object that we're, the substance that we're putting in there. So here, let's change some colors. Let's make the left side blue to represent water. Oops, I almost wrote an A, MCAT, but it's a delta triangle. So blue is water, and red is the unknown substance that we are adding into there. All right, we need to identify what we're looking for. So we're looking for what the substance is. So we're looking for the substance. So in other words, we're going to take a look at this table here, and we're going to identify which substance it is based on what the specific heat value is. Like, for example, if it's 0.902, then this substance would be aluminum. We don't know if that's the case, though. So what we're looking for is the specific heat. That is our variable that we're solving for, the specific heat of the substance. So let's just rearrange this equation for that. It looks like we can divide both sides by the mass of the substance and the change in temperature of the substance, which would cancel on the right side and transfer over to the left side. In all, what we're going to have is the specific heat is going to equal mc delta T of water divided by m delta T of the substance. So let's plug in some numbers here. The mass of the water was written to be 100 grams. So 100 grams, and the specific heat of water is given to us in that table. It is 4.184, according to this table, joules per gram degree Celsius, which notice the grams are going to cancel. And then we are multiplying by the change in temperature. So we need the final minus the initial. So the final temperature of the water is 32.5. So 32.5 degrees Celsius, and we're going to subtract out the initial, which was 20 degrees Celsius. So all of that's going to be in degrees Celsius, and then notice the degrees Celsius is going to cancel itself. And then we're dividing all of that by the mass of the substance, which was 360.4 grams, and we're multiplying that by the change in temperature of the substance. So we need the final temperature of the substance, and the key here is that the final temperature of the substance is also the final temperature of water. So we also get 32.5, and we're going to subtract out the initial temperature of the substance, which looks to be about 100 Celsius. Now, there is one mistake I've made. Down here, this is going to get us a negative number, which is fine. But the problem is I forgot to carry over from our original equation, that negative sign. So let me just put that negative sign in there. That's going to cancel the negative sign given by that change in temperature expression, giving us a positive value in the end. Now, this is a complicated equation here, so it's probably good that I show you how I would plug this in the calculator. Now, this isn't a scientific calculator, so let me just show you how I would go about it. I would first probably find the difference between the 32.5 and the 20. So 32.5 minus 20 is 12.5. Then I'm going to multiply it by the 4.184, and then multiply that by 100. And what I could do is I could just write that number out. So 5,230. So in the top we have 5,230. And right now it's in joules. And then we need to do the bottom. So what we're going to do is we're going to do the temperature first. So the temperature is going to be 32.5 minus 100. We know that negative is going to get canceled, so we can kind of just ignore it right now. And then we're going to multiply that by 360.4. And in the bottom we get 24,327. So all over 24,327. And that's in grams times degrees Celsius. And notice our units at the end are going to be joules per gram degree Celsius, which are the units of specific heat. So that's one way of checking our work and making sure that it is correct. All right, so now we can plug it in the calculator. We can take move this calculator over here now. We're going to take 5,230 and divide that by 24,327 equals, and we get 0.215 joules per gram degree Celsius. Everything was using 3 or 4 sig figs, so we're going to keep that in 3 sig figs. We're going to look over our table, and our table, it doesn't have none of them have the exact value we found, but of course we all understand that the last digit is not for sure known. It's where our uncertainty is. So we're going to take a look at tin here, because tin, wow, tin has a value of 0.213, which is basically close enough. So what we're going to write as our answer is that this is tin. Problem 13 is finding out what the change in enthalpy is, and also identifying whether it's endo or exothermic reaction. So for this, we're going to notice that the change in enthalpy is negative. That means it's going to be exothermic because it's releasing energy into the environment. The final is less than the initial enthalpy or energy that it had, so it gave up some of its energy into the environment. So it's exothermic, and technically the only justification we need is that because the change in enthalpy is negative. That's all the justification we need. All right, now the question is, if we react 35.5 grams of fluorine with unlimited hydrogen, how much energy will either be released or absorbed? One thing we should notice is that it was grams given, not moles, and this value of enthalpy is actually per, so negative 542 per every 1 mole of fluorine, because the coefficient in front of fluorine is a 1. So we need to first convert fluorine into moles. So we're going to start with 35.5 grams of fluorine, and we're going to multiply it by something that will convert it to moles, which we should know by now is the molar mass. 1 mole of fluorine, and we need to know how many grams of fluorine 1 mole is. Fluorine's molar mass of 1 fluorine atom, or 1 fluorine, single fluorine, is 18.9984, but we're going to be multiplying that by 2. So let's take out our calculator. 18.9984 times 2 is 37.997. 37.997. That's going to get us moles. What we're then going to do, and we can just extend this, is that we know that negative 542 kilojoules of energy are going to be released for every 1 mole of fluorine. So we're just going to multiply it by that ratio, and it cancels the moles of fluorine and is going to give us, in the end, kilojoules. So we got 35.5 divided by 37.997 times 542, and that equals 506. Now, 3 sig figs is 506. 506 kilojoules of energy. Now, it says either released or absorbed. This is going to be released. So if you want, you can keep that negative there. Problem 14 is creating a claim evidence reasoning to answer the following question: is freezing exo or endothermic process? So the idea is if you had some water, so we'll just draw a drop here of water, and if this water froze into an ice cube, would the system, which we're going to call this is the system, did the system lose or gain energy from its environment, from its surroundings? Now, water, liquid, has more kinetic and thermal energy than ice does, or the solid form does. So in order for that to happen, this had to radiate out its energy into its environment. So that means energy had to go from the system to the surroundings. This is the definition of an exothermic process. So for our claim is going to be that freezing is exothermic. And then we're going to say that the evidence portion is going to be this talk about systems and surroundings. So, or this talk of that the energy must have left it. Since solid substances have less thermal energy than their liquid state, energy must have left the system and gone to the surroundings. That was just the evidence. The reasoning, we're going to tie in the definition of what exo and endothermic is. So that's why it says here at one point for using the definition of exo and endothermic in your explanation. So I maybe abuse the word sense, but I'm going to use it again. Sense. Exothermic processes are defined as a process where heat goes from system to surroundings this process been exothermic. So the key here is that in your reasoning, you should have the definition of endo or exothermic put in there. Le Chatelier's principle. So this is about equilibrium reactions. We have a chemical reaction between sulfur dioxide and oxygen, creating sulfur trioxide. This is an exothermic process in the forward direction. We're going to create a Cramer-Evans reasoning statement to explain how you could favor the production of sulfur trioxide. So we're going to try to talk about how would we change the conditions to favor sulfur trioxide. There's a few ways to do this. One way of favoring the forward direction would be to, so I'm going to bullet point this, add more sulfur dioxide or oxygen. By adding more reagents or reactants, it's going to favor the forward direction of this. That's just one way. There's a couple other ways. Another way is that we can adjust the pressure. Notice all of these are gases, and so we're going to look at which one has the least amount of moles of gas. This has 2 plus 1, so the left side has 3 moles of gas and the right side has 2 moles of gas. That means the right side has the fewer moles of gas. And the rule is, if we increase the pressure, it will favor the side with fewer moles of gas. So if the right side has fewer moles of gas, and that's what we're trying to favor, we need to increase pressure. And finally, this is an exothermic reaction, which means if you think about it in the reverse direction, there's heat. In the reverse direction, heat is needed to be added to go backwards. So if we remove the heat, it can't go back as much. It cannot do the reverse direction as well because there's no heat. So what we're going to want to do to favor the production of sulfur trioxide is remove heat. So we're going to cool this down. So you're going to choose one of these and make a Cramer-Evans reasoning for it. The final problem is acids and bases. It's a titration, which you're going to be doing in the lab. So you're doing a titration of an unknown sample of hydrochloric acid. You take 5.00 milliliters of hydrochloric acid solution and add it to a flask, along with additional water, which isn't going to matter at all, that point right there. In your burette, So your burette starts with 46.2 milliliters of sodium hydroxide. You dispense until you have only 23.9 milliliters left of sodium hydroxide. What was the concentration of hydrochloric acid solution? To do this, first thing we're going to do is find moles of sodium hydroxide. To do that, we first need to find what the volume of sodium hydroxide is, because remember, molarity is equal to moles divided by a volume. So if we want to find moles, we just multiply both sides by volume. So essentially, if we take the molarity and multiply it by volume, we're going to get moles. But we need to know what the volume is. For that, we're going to take 46.2 milliliters and subtract out the 23.9 milliliters. And that will get us the volume of sodium hydroxide. Pulling out the calculator again. 46.2 minus 23.9. 22.3. 22.3 milliliters. Now, since we're multiplying a molarity times a volume, we need to convert that into liters, so this is 0.0223 milliliters. All right, now we have everything to find the moles. So what we're going to do is moles of sodium hydroxide is going to equal the molarity, which was 0.100 moles per liter, times our 22, whoops, my bad, mistake. I need to use the liter one, so 0.0223 liters. See, that cancels liters and gives us moles. That's just going to move the decimal one space more over, so 0.00223 moles. Now, the reason we need to find moles is because we need to find out how many moles of acid we had in that 5 milliliter sample. So inside that 5 milliliter sample, how much acid, how many moles of acid did we have? We can find that out from using the chemical equation. So the chemical equation for this reaction is sodium hydroxide plus hydrochloric acid react on a 1-to-1 basis to create H2O and NaCl, or salt. So it's a 1-to-1. What's important about that is finding the mole ratio, which is 1-to-1. So we had 0.00223 moles of sodium hydroxide. To do this properly, let's multiply it by the mole ratio, which is 1 mole of what we have, which is the sodium hydroxide, and 1 mole of what we want, which is the hydrochloric acid. And notice the moles of sodium hydroxide cancel, and we get moles of hydrochloric acid, so it's the same number. Last step is we are going to use this moles and the volume of acid that we had to find its concentration. So the concentration is going to equal moles divided by volume. So we're going to take our 0.00223 moles of HCl and divide by our concentration, or our volume, which was 0.005 liters. Notice I already took those milliliters and turned it into liters. Let's plug that in the calculator. 0.00223 divided by 0.005, and what we get is 0.446. 0.446 molar, so moles per liter. All the numbers we worked with have had at least 3 sig figs, so we're going to keep it 3 sig figs, and there's our answer.